Hi, James here. This is a video of all of my solutions to Maths 2016 problems. I'm not expecting anybody to watch all of this video. It's very long and you've got better things to do. I've put links in the description to each question from Maths 2016 so that you can skip through to the ones that you're interested in. Okay, let's go. Okay, in this first question we're given a sequence an, and we're told the first term is 1 and then the subsequent terms are defined by this relationship. So every term is L times the previous term after the first one. And the question asks us for the product of the first 15 terms of the sequence. Now there's a sort of problem here. It's very easy to get carried away writing down the terms of this sequence and then think, aha, I know what this is. This is a geometric series. That's true, it is a geometric series. Of course, the thing we normally do with a geometric series is we add the terms together and we have some equation for what happens when you add together the first 15 terms of a geometric series. Here the question, what's the product of the first 15 terms? The product means we want to multiply these things together instead. So this is a slightly different question to the standard what's the sum of these terms of a geometric series question. This is looking at the product of these terms. Okay, I need to do some laws of indices to combine these together to be, this is L to the 0, this is L to the 1, L to the 2, and so on up to L to the 14. So when I multiply all those together, I get L to the 0 plus 1 plus 2 plus 3 plus 4 up to 14. And now this looks less like a geometric series and more like an arithmetic series. Upstairs, anyway, up in this exponent, that looks like an arithmetic series to me. And the sum there is 14 times 15 over 2, I think, which is 105. So my product is L to the 105, and my answer is D. I think it's easy to get carried away by spotting that it's a geometric series and then adding the terms together without thinking about what product means in this question. Let's just have a quick think about what you would get if you added them together. I suppose you'd get L to the 15 minus 1 over L minus 1 or something like that, which isn't one of the options. So maybe that's a kindness of the question. Okay. This question is about a hexagon. And we're told that it's an irregular hexagon with all sides of equal length. It's worth unpacking that a little bit. I suppose the hexagon has corners here, 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 and here, and we're told that the sides are equal length. Okay, but it's irregular, so I suppose the angles are different. And actually that makes sense, because some of these angles come from the square, they're right angles, and some of these angles are, well, not right angles. So this is not a regular hexagon. I guess irregular can mean just has all its angles different and all its sides the same length. Okay, and we're told that it's inside this square of side length 1. So this length here is 1. This picture is not to scale. We're asked to find the length of one of the hexagon's sides. So that would be this length here, which is, I'll call something like x. In general, it's a good idea to give names to things if you want to try and solve them. I don't know any facts about hexagons. In fact, the only way into this question I can see is to use this fact that they've told me, that the sides of the hexagon are equal length. In particular, I suppose, well, it's got a line of symmetry down this line. This picture has a line of symmetry here. So it's not very interesting that this line is the same length as that line, I suppose. What is interesting to me is that it's the same length as this line here. This is also x. Okay, what can I do with that? Well, I suppose I could look at this little triangle over here. I haven't used the fact that the side length of the square is 1 yet. Maybe if I looked at this bit over here, I could say I've got this small triangle down in this corner. I don't know many facts about hexagons, but I know lots of facts about triangles, especially right-angled triangles. And this long side here is x, and then this short side is going to be, I think, 1 minus x. Because the whole side length is 1, this bit is x. Okay, and now I've used both facts. I've used the fact that the sides of the hexagon are equal length, and I've used the fact that the side length of the square is 1. So I've got this small little triangle here. I suppose this is 1 minus x as well. This is also x, there's 1 minus x. A little isosceles triangle here. And now I'm going to use Pythagoras to work out the side length of that triangle. Well, I suppose I'm going to use Pythagoras to work out the side length of the hexagon too, by working out x. Okay, so I'm going to work out 1 minus x squared plus 1 minus x squared is equal to x squared. That's Pythagoras for this little triangle over here. I'm going to expand that out, and I'll get 2 minus 4x plus x squared is 0. Now, do I feel like completing the square or just writing down the quadratic formula? I think I feel like completing the square on this one. It's good to have a variety of techniques, right? So this is this, x squared, x minus 2 squared gives me these terms. Also gives me a 4, so I need to subtract 2. This is 2. So x is 2 plus or minus the square root of 2. I want x to be smaller than 1, I think. So I want x to be 2 minus root 2. X is definitely smaller than 1 because it's part of this side of the square. Okay, so my answer is B for question 1B. This question is about a circle, and we'd like to know whether the origin, that's the point 0, 0, lies inside or outside this circle. It's got equation x squared plus ax plus y squared plus by equals c. And we'd like to find a condition for when the origin is precisely inside that circle. What values of c does that happen for? And there's some different options here, different conditions on c in terms of a and b, or just saying that c is positive. So I think we need to find out what this circle looks like, where it is, how big it is, and then we can start to think geometrically about whether the origin is inside or not. So I'm going to make this look a little bit more like the equation of a circle. I'm going to complete the square. So I'll need to add in a squared over 4, and I'll need to add in b squared over 4. That's true, I think. This is a circle with centre minus a over 2 minus b over 2 from this part, and with radius root c plus a squared over 4 plus b squared over 4. Okay, very nice. Right, so if c is very negative, then this radius isn't a real number. So this is not even a circle at all. If a and b are 0 and c is minus 10, then that's not a radius. So there's no circle whatsoever. Okay, so I definitely want that thing inside the square root to be positive. Okay, but more than that, we want the origin to be inside this circle. Let's draw a picture. Here's what I'm imagining. The centre is over somewhere like that, and there's a circle around there. And the question is the origin inside that circle? And the normal way that I use to decide whether points are inside a circle or not is to measure how far away they are from the centre, and then say, well, that circle is all of the points that are closer to the centre than the radius. That's just how circles work. So here, for example, the origin is not in the circle, it's too far away for this particular picture with that particular radius. Whereas if the picture looks more like this, nice large circle, it's a terrible circle, then the distance to the origin would be less than the radius. So that's the test that I'd like to use. I'd like to test whether the distance from the centre to the origin, so that's distance centre to origin, is less than the radius. If it is, then the origin is inside the circle. Okay. Going to do a little bit of calculation to work out the distance from the centre to the origin. That's, I think, a squared over 4 plus b squared over 4 square rooted. Thinking about the size of this vector, if you like. I want that to be less than root c plus a squared over 4 plus b squared over 4. But this happens, I could solve this inequality, I suppose, but I can already see that this happens whenever c is positive. If c is positive, then this right-hand side is just bigger, because it's the square root of a bigger positive number. So I can rearrange this inequality a little bit, square each side, subtract the common terms, and I'll find that This happens whenever c is positive. Quick check, in all of those cases, this radius does actually make sense. This is a circle. Check your answer at the end, I suppose. But yes, whenever c is positive, then this radius will be big enough that the origin is inside the circle. Very quickly, another approach for doing this question is to think about the critical value for c, to imagine changing c through the real numbers and thinking about how it changes from having the origin inside to outside the circle or vice versa. At the critical threshold, the origin will be on the circle. It will go from being outside to inside via the boundary of the circle. In that critical case, 0, is on the circle. So in that critical case, x is 0, y is 0, and on the left-hand side, everything cancels. So c is 0. That's a clue that c equals 0 is an important value of c, no matter what a and b are. So that's a quicker way to spot perhaps that a and b are sort of not important in the final answer here. So shortcuts to the answer being A. So here's an interesting question. We're asked to find all the solutions to cos to the n x plus cos to the 2n x equals 0 in the range x between 0 and 2 pi. This was back in the days when questions used radians. If you like, you can imagine that this has 360 degrees. Okay, same question in degrees. And we're told that n is an integer that is bigger than or equal to 1. Okay, and I think the interesting thing here is that the options all seem to have the possibility here that the number of solutions, in cases D and E, the number of solutions might depend on whether n is even or odd. That's interesting. We're going to get there when we get there. Let's try and solve this. So we've got cos to the nx plus cos to the 2nx equals 0. Now, after playing around with this for a little bit, I think you find that we could try small values of n. We could try to use some cosine facts about the cos squared is 1 minus sine squared fact. This thing reminds me of cos squared. Plugging in 1 minus sine squared, though, is quite a lot of work. Raising that to the power of n is not very fun. Instead, I'm going to suggest that we think about this as some object, and then this is the square of that object. I'm going to make a substitution. I'm going to sub u as cos to the nx. Okay, so that simplifies this equation. Of course, some of the complexity is hiding in this fact here. We're going to have to interact with this in a minute when we come back to solve for x. But in terms of u, it makes the equation nice and simple. U plus u squared equals 0. Great news. That means u equals 0 or u equals minus 1. Okay, solving that quadratic. Okay, backtrack a little bit. We're interested in cos to the nx equals 0 or cos to the nx equals minus 1. Okay, so I'm starting to see why odd or even might matter for n, because if n is even, then I never get any solutions over here, because cos to the even power is always going to be a positive number. Okay, so I'm leaning towards options D and E. I just feel like it should depend on n being odd or even. Okay, let's actually count how many solutions we're going to get. So this case will always be cos x to the n is only 0 if cos x is 0. That's not so bad. So this is when cos x is 0, which I think is just for pi over 2 or 3 pi over 2 in radians, or 90 degrees and 270 degrees in degrees. Whereas over here, I suppose we're interested in solutions where, so here we get more solutions, don't we? But only if that thing on the left can be negative. Interesting. I suppose, so if n is even, I've said we get no solutions over here. If n is odd, then I suppose I want cos x to be minus 1. If cos x is minus 1, then when I do minus 1 to an odd power, I'll get minus 1. I think that's the only way to get minus 1 out of this equation. Okay, When is cos x minus 1? Well, that happens when x is pi, or 180 degrees if you use degrees, which gives us an extra solution when n is odd. So I think 2 solutions all the time, including even or odd n, and then 1 bonus solution when n is odd. I think that gives me D for question 1D. Okay. Okay, this question is about curve sketching. This is how we do curve sketching questions in the multiple choice questions of maths. We can't mark your sketch for a multiple choice question, but we can give you some plausible options and ask you to choose which one is the right graph. So here we've got a graph of x minus 1 squared minus cos pi x, and 4 other graphs, and we've got to choose which one is the right one. This question is back from when math questions use radians. So if you like degrees, then you could imagine that this said cos of 180x in degrees, I suppose. Okay, if you'd rather. To do this question, we're going to need to understand the parabola part of y and also understand the cosine part of y. Here are the options, by the way. So we can look at these options and think about which of these look plausible. I think 4 of them look like a kind of broadly parabola shape with some wobbles on. Actually, I suppose C doesn't have any wobbles on, which I was expecting kind of cosine wave wobbliness around there, so I'm a bit suspicious of C. D doesn't seem to have any parabola shape to it at all, so I'm suspicious of that one as well. And then it looks like A, B and E, we're going to have to think about the amount of wobbliness or something. That's my overview of this question. Okay, let's try and make that a bit more concrete. We could look at values, perhaps look at values when x is 0. We could try and solve for y equals 0, but that looks quite tricky. So I'm going to take the easy one first and plug in x equals 0. That gives me y is 1 minus cos of pi x when x is 0. Cos of 0 is 1, so this is 1 minus 1. 1 minus 1 is 0. Okay, so when x is 0, y is supposed to be 0. And that's going to rule out D, which I was suspicious of, and also E, because this says it goes through the origin. These two do not seem to go through the origin to me. Okay, so that leaves us with 3 that go through the origin, A, B and C. I'm still suspicious of C. I haven't ruled it out yet, but I'm still suspicious. Right, I mean this just looks like the parabola. Is this the parabola x minus 1 squared? Oh no, because that's got a repeated root at 1, and this doesn't have a repeated root. Maybe it's x minus 1 squared minus 1. Okay, I'm very suspicious of C. Let's see. So the reason I thought this looked like x minus 1 squared is because it's got this kind of minimum at 1. I suppose there's no labels on the x-axis, so we should try and see what we can infer from the shape of the graph. I know that parabolas are sort of symmetric. They have a minimum or a maximum in the middle. These curves, I mean, I don't want to say maxima or minimum because there might be a maximum or a minimum, but maybe there should be some sort of symmetry about x equals 1. You know, so parabolas have this symmetry in x equals, this parabola has symmetry in x equals 1, reflectional symmetry. And also, I suppose cosine pi x has symmetry about x equals 1 as well, because the cosine wave has symmetry about x equals pi, where it's minus 1. There's a reflectional symmetry there as well. Okay, so I'm expecting, let's try and draw that. Cosine looks like this. So when x is 1, cos of pi x also has this kind of reflectional symmetry. I think that lets me infer where 1 must be on these pictures if they're going to be the graph of this function. So on C it would have to be about here, right? It's got to have a line of reflectional symmetry in x equals 1, so it's going to have to be in the middle of this picture. Similarly here, I think these might have the same scale as each other actually. We're not told that, but it seems reasonable now that I've put in those midpoints of the curves. Okay, so that's where I think x equals 1 is in the line of symmetry on these curves. Okay, what else do I want to check? I think I'd like to check what the value is at x equals 1. Now that I've kind of worked out where x equals 1 is, I'd like to think about what the value is over there. So y is 1 minus 1 squared is 0, minus cos of pi is minus 1, so that's 0 plus 1 is 1. Okay, so at x equals 1, it's supposed to go through x equals 1, y equals 1, which is a point up here, so not B, not C. I think that only leaves A. Okay, so we've got a solution of A, and if I went and sketched that, I think that looks sort of how I was expecting, a kind of parabola shape, but then with cosine wobbliness added on, so that there's a peak of the cosine wobbliness, minus cosine pi x is positive when x is 1, and there's a peak of the wobbliness that coincides with the minimum of the parabola. Okay, bit of a mouthful there, but I think A. Okay, getting a little bit harder now. This is question 1F from Math 2016. We're told that n is a positive integer, and we're asked, more or less, whether x squared plus 1 is a factor of this horrible polynomial in x. So it's got these powers of n in here as well, look. It's sort of the difference of two nth powers. I'm not really sure about that yet. And we're asked whether x squared plus 1 is a factor or not. Seems pretty tough. Seems quite hard to tell whether x squared plus 1 is a factor. I suppose I know a fact about factors of polynomials, but that only works for things like x plus 1 or x plus 2. The factor theorem tells me that if minus 2 is a root, then x plus 2 is a factor. Stuff like that. That doesn't help me here because I'm looking at x squared plus 1, which isn't the same thing. I suppose it's not the same thing unless I do a little bit of work to do some sort of substitution. So I could take this and say, well, hang on. What if I write u equals x squared? Now the thing that I'm looking for says u plus 1 is a factor. That looks to me more like the sort of statement we make from the factor theorem. Okay, so I should plug in u equals x squared and see whether u plus 1 is a factor. That makes it feel a bit more like a factor theorem kind of question. What am I going to get? I'm going to get 3 plus u squared to the n minus u plus 3 to the n, u minus 1 to the n. Okay, and I want to know, is u plus 1 a factor? So I should check whether u equals minus 1 is a root. Okay, so that's going to involve plugging in minus 1 and seeing whether or not I get a solution to this thing equals 0. Okay, so let's plug in u equals minus 1. The polynomial will give us 3, then u squared is 1 to the n here, plus u plus 3 is 2 to the n. U minus 1 is minus 2 to the n. So this is 4 to the n minus... Now, goodness me, that looks a bit like 4 to the n, this second term, but there's a lot of minus signs. I'm going to keep track of my minus signs here by putting some minus 1s out. I've got n of them, the minus signs. And then I've got, I suppose, 2 to the n, 2 to the n left over, so that's 4 to the n. I want to know whether this is 0. That will tell me whether u equals minus 1 is a root or not. Okay, I think this is 0 if and only if this whole pile of minus signs all cancel out with each other. I want this one. I want 4 to the n minus 4 to the n, but I want all of these to just go away. So I suppose I want minus 1 to the n to be 1. So that this reads 4 to the n minus 4 to the n, which is 0. Okay, I think that means I want n to be even. If and only if it's even. If n is odd, then this is minus 1. If n is even, then this is 1. So even n is good enough. And then u equals minus 1 is a root. So u plus 1 will be a factor, which means that x squared plus 1 will be a factor of the original polynomial by substituting in. So substitute x squareds for u's, factorise out u plus 1 using polynomial division, and then substitute back in x squareds again. Okay, it gives me even n. So option B. A crucial step here is that this polynomial only involves x squareds, so that once I've done the substitution, I get a polynomial out. It doesn't have any u to the 1/2 powers in there, so I can use the factor theorem on this polynomial. There's a slightly different approach, which uses complex numbers. Now, complex numbers are not on the MAT syllabus, but a slightly different approach would be to look at this and say, well, if x squared plus 1 is a factor, then I want x plus I, x minus I to be a factor, factorising x squared plus 1 over the complex numbers. So I should check whether plus and minus I are roots. That's not really on the MAT syllabus, that approach. It gives you the same answer and it works. If you're happy with complex numbers, then that's fine. If you're screaming at the TV set because you don't like the idea of factorising x squared plus 1, then that's fine too. Here's an alternative solution using u equals x squared. Okay, but my answer is B. Okay, here's a fun question. We're given a sequence xn, which is defined in some way I've never seen before, and we're asked to work out this sum. Look at this, the sum from k is 0 to infinity of 1 over xk, an infinite sum of reciprocals of the terms of the sequence. So that looks pretty scary. This looks pretty scary as well, this definition of what xn is. So I think my way into this question is going to have to be, I'm going to work out some terms of this sequence, desperately hope that I can spot a pattern, and then extrapolate from the pattern to work out what this sum is. Hope that I can do this sum and get one of these 5 answers. That's really all I've got right now. Okay, I'm told the first term of the series. I'm told that x0 is 1. That's pretty good. Okay, and then I suppose I could work out x1. In words, I think this means every term of the series is equal to the sum of all of the previous terms. This is x0 plus x1 plus ... plus xn minus 1, all the way up to xn minus 1. So I should add together all of the previous terms. Here that means that x1, well, there's only one previous term, is 1, and then x2 is going to be 1 plus 1. 1 plus 1 is 2, welcome to the maths live stream. X3 is going to be 1 plus 1 plus 2 is 4. X4 is 1, 1, 2, 4, adds up to 8. And now I've spotted a pattern, so I can relax a little bit. I've spotted that after the first couple, each term seems to be twice the one before. I think I can actually prove that each term is twice the one before. Maybe I'll come back to that in a minute. Let's just finish off doing the question. Let's say you spot this fact that each term seems to be twice the one before. Then this infinite sum we're asked to do, that's equal to 1 over 1 for x0, 1 over 1 for x1, 1 over x2, 1 over x3, 1 over x4, and so on, where this first term is 1, this one is 1, 1 plus 1 is 2, and then there's this infinite sum, a half plus a quarter plus an eighth plus a 16th. This is a very famous geometric series sum, where we've got a half, quarter, eighth. That adds up to 1 as well, so ... That also adds up to 1. You can do the geometric series if you want to. Each of these terms is a half the previous term. Okay, 2 plus 1 is 3, so my answer is D. That's enough to get the marks in this multiple choice question, but I think it's worth proving that after the first couple, each term is twice the term before. Let's think about that. If xk is equal to xk minus 1 times 2 for some k, then xk plus 1 is equal to, well, by definition it's the sum of all of the previous ones. But hang on, so is xk, more or less. So xk plus 1 is x0 plus x1 plus ... plus xk, but all of this stuff was xk as well, because that's xk by definition. So this is 2 times xk. There's 2 lots of xk. Oh, actually, I don't need this at all, do I? I don't need this. Xk plus 1 is just equal to the sum of all the previous terms. By definition, that's xk, plus a new term on the end, because this sum has got slightly more terms in now, another xk. That's 2 times xk. Okay, brilliant. So that's a little proof that each term after the first few is twice the term before. Okay, this question is going to test whether we can integrate polynomials and also whether we can draw polynomials. So we've got f of x is a minus x squared. We're told a is positive, so this quadratic looks like this. That's f. And we've got a fourth power kind of thing over here, x to the 4 minus a. That's going to be g. And we're asked for which values of a is this area bigger than the area here. So we're going to need to integrate some polynomials. And let's quickly work out where these points of intersection are. This one is square root of a minus square root of a. Oh, excuse me, minus square root of a. This one is the fourth root of a and minus the fourth root of a. Which one should we do first? Let's do this one first. So here we've got to find that area. So we need to integrate f. I'm going to do that over here. So that's looking for area of integral of a minus x squared between minus root a and root a, which is going to be ax minus x cubed over 3 between root a and minus root a, which is then a to the 3 over 2 minus 1/3 of a to the 3 over 2 is 2/3 a to the 3 over 2, and then the other side gives us another 2/3. That's going to be 4/3 a to the 3 over 2 on that side, in the left corner. And on the right side, I've got to do this integral. At some point I'm going to need to remember that here the curve is below the line, so I'll get a negative number when I do the integral, but areas are positive. So I'll need to remember to throw a minus sign in at some point. But I'm going to go ahead and do the integral as I normally would, without worrying too much about that just yet. So that's this integral to do. That's x to the 5 minus 5 minus ax between the limits of a to the quarter up the top and minus a to the quarter down here. That gives me a to the 5 over 4. 1/5 minus an entire thing is minus 4/5, and then the other side gives me 1/5 minus another plus another minus plus another 4/8, I think, with a minus sign. My area is then going to be plus 8 over 5, a to the 5 over 4. Now, what do I want? So we bring them from the left side and the right side to fight in the middle. I want 4/3 a to the 3 over 2 to be bigger than 8/5 a to the 5 over 4. Okay, when does that happen? Well, let's make them fight. So I should look at moving the a's over here. So I'll get a to the 3 over 2 is a to the 6 quarters. So if I divide both sides by a to the 5 over 4, a is positive, then I'll get a to the quarter over here, 6 quarters minus 5 quarters. And over on this side, if I multiply up, I'll get 3 times 2 over 5 is 6 over 5. Just simplifying this, which I think means that I want a to be bigger than 6 over 5 to the 4, which is option E. Precisely. Okay, quick test. Can we do those integrals? Can we plug in limits? And then can we simplify inequalities out the end using the fact that a is positive? I get E. This is a great question. This wants us to find the maximum of a particular function subject to a particular constraint. This is a whole branch of mathematics that if you study maths at university, you will almost certainly have the option to study this sort of mathematics. Okay, here there's sort of different approaches we could use. We could think about this in terms of algebra, or we could think about it geometrically. I'm going to try and do both methods on this whiteboard. Let's have a go at geometrically first. We're told that x squared plus y squared is less than or equal to 1. That means that the point xy is inside or on the circle, the circle with radius 1 centered at the origin, the unit circle. Perfect. Okay. And then we're given a line y equals I'm going to write it as y equals, if we were looking at the line ax plus by is c, then that's y is equal to c over b minus a over b x, provided b is not 0. And we'd like to make c really big. We'd like to maximise c. So I suppose this is saying, given some line, a and b are both positive, I suppose, so not 0, let's say. This has got a negative gradient, so we're looking at some line like this, and saying, what's the largest I can make c? What's the largest I can make this y-intercept up here? So I want to make the y-intercept really big, such that there's still a point inside or on this unit circle that's on the line. And I think geometrically, the idea is that I want to move this line, I want to greedily make this nice and big by moving this line up until I'm getting so greedy that this is just tangent at a single point. And that's the highest I can move the line, because when I move the line up any higher, there's no points inside the circle that lie on the line. If I move the line lower, then I'm missing out a little bit on some c that I could be getting by moving that line nice and big. This is the value of c over b up here. Okay, so now I've got to do a geometry question to work out, I know the origin of this circle, I know the radius of this circle, I know the gradient of this line is minus a over b. I've got to find this point, and I've got to find the value of ax plus by at that point, which is the number c. Okay, I'm going to try and do that algebra very quickly. So, very quick algebra. The tangent's at right angles to the radius. So the gradient of that radius, must be minus 1 over the gradient of the tangent, which here is b over a. Okay, so my gradient of my radius is b over a. That's the triangle that looks like, if this is the radius, then the angle there is just the right angle that you would find in a triangle with sides b over a. That's what gradient of the radius might mean, that the gradient of the radius would be this angle, such that the angle is the angle in the triangle with sides a and b. But I know that the radius of this thing is actually 1. So it's not actually this triangle, it's a similar triangle to this. I know that it's a similar triangle to this with radius, with hypotenuse 1, x coordinate proportional to a, y coordinate proportional to b. This particular triangle I've drawn has side lengths like this. I'd like to scale down that triangle to work out, this triangle in here is similar. I'd like to scale it down. I'm going to scale it down by dividing everything by a squared plus b squared, because then I'll get a triangle which has that magic hypotenuse of 1. I know this circle has radius 1, so I know this is 1 over here. This is a over root a squared plus b squared after I've scaled it down. This is b over root b squared plus a squared. Those are my x and y coordinates of this point that I want. Once I've got the x and y coordinates, I can go and plug them into ax plus by equals constant, or thing I'm trying to maximise, and I work out that a times a over root a squared plus b squared, that's a times x plus b times b over a squared plus b squared, my word, is equal to this, which is a squared plus b squared over root a squared plus b squared. That is equal to root a squared plus b squared. Phew, my goodness. Okay, which is c. Okay, that's the geometric method. Very quickly, 2 for the price of 1. I'm going to try and show you an algebraic method here, without thinking about circles. I'm told that x squared plus y squared is at most 1, and I want to make ax plus by really big. A and b are positive numbers, so I want to make x as big as I reasonably can, right? If x squared plus y squared is less than 1, then make x bigger. Or you could choose to make y bigger, I suppose, but do something. Don't settle for less than 1. If x squared plus y is less than 1, then you can definitely make this bigger just by making x a little bit bigger, until you get up to x squared plus y squared equals 1 at max. So I want to make this thing x squared plus y squared equal to 1, and I want to use that to rearrange for what ax plus b, and then y is going to be root 1 minus x squared, and I want the maximum value of that. And now actually finding the maximum value of that is not on the math syllabus. I don't expect you to be able to differentiate that, but if you follow it through, then you find that the maximum value of that function happens when x is a over root a squared plus b squared. I've missed out a b in here. Yes, okay. Calculus problem, bit harder than math. Perhaps not the best way to do this question. Find the maximum value of this function. Okay. Okay, this last multiple choice question is about integers, that's whole numbers, and it defines two new functions. This is a capital pi, by the way. You know pi, this is the capital pi. Capital pi of n means the number of distinct prime factors of n. Okay, so they give us some examples. Pi of 8 is 1, because 8 is 2 to the 3, so it only has one distinct prime factor, 2. And pi of 6, well, pi of 2 times 3 here, that's got two distinct prime factors, 2 and 3, so that's 2. Okay. Pi of 10 is 2, because it's got two distinct prime factors. Pi of 100 is 2, okay, things like that. And they also define x of n, which is maybe not my favourite name for a function. You're probably used to x being the input to functions, but never mind. X of n is going to be the final digit of n. Maybe f of n for final. Never mind. We were using f for different questions. Okay, so for example, x of 8 would be 8, x of 16 would be 6. It's the last digit in base 10, I suppose. Which of the following statements is false? Okay, so there's a lot of thinking there before you even get into the question about these new functions feel quite strange. The final digit one I kind of get, I can work that out. The other one requires me to factorise the number, so that's pretty tricky, and then count the number of distinct factors. Okay, they want to know which of these statements is false. That means that 4 of them are true and 1 of them is false. Okay, so let's try and identify which ones are true. Are there any obvious ones which might be true to start off with? 80% of them are true, so I can sort of guess in some sense. Let's look at that last one because it's the shortest. If pi of n is 2, all values of xn are possible. Okay, so this says if number has exactly 2 distinct prime factors, then all final digits possible. Okay, that sounds kind of true. Let's see if we can make all of the final digits out of using numbers that have pi of n as 2. I'm going to start with 0 because I was already thinking about 10. X of 10 is 0 and pi of 10 is 2. What else can I have? So I'm thinking of numbers where you multiply together two primes. I guess I could use the power of one of the primes if I wanted to. That might be a good idea. And I want to try and make all of the final digits. For example here, x of 21 is 1, and that's 3 times 7. Pi of 21 is 2. 2, how am I going to make 2? Well, I think x of 22, I'm thinking of 2 times 11. Small numbers are easier to work with here. 2, 3, how do I make 3? Can I do 3? Oh, hang on, I can do 33, can't I? And I think I'm going to be all right. A pi of 33 is 2 because it's 3 times 11. Okay, what do I want next? I have x of 14 is 4, and pi of 14 is 2 because it's 2 times 7. For 5, I think I'll use 3 times 5, so 15 is 5. For 16, 6, I can't use 16 because pi of 16 is 1. For 26 though, that's nice because x of 26 is 6, sorry, and that's 2 times 13. What do I want here? So I don't want 17 because that's got 1 prime factor. 27 has got 2 prime factors. 37 is prime. 47 is, I think, prime. 57 is 3 times 19. So that's got exactly 2 prime factors. Wow, I had to go a long way to find that one. X of 8, I don't want 18, I like, because that's got final digit 8, and it's got just 2s and 3s, so pi of 18 is 2. And then that 9, I don't want 9 because it's only got one prime factor. 19's only got one prime factor. 29's only got one prime factor. 39 has got 2 prime factors and final digit 9. Wow, so lots of work later, this one is true, which in the backwards world of the logic of this question means that the answer is not E, because E is not false. Wow, I had to do a lot of work to find that. Okay, let's look at some other ones. D, if pi of n plus x of n is equal to 2, we cannot tell if n is prime. Okay, so what have I seen so far? I've seen an example, x of 10 is 0 and pi of 10 is 2. I'm looking at the things below to see if I can spot ones where x plus pi is equal to 2. That's an example where not prime. Do I think this is always true? So it could be the case that this is false and we can tell if n is prime. It now looks like if we can tell, then the conclusion is not prime. If we can tell if n is prime. I suppose they mean just from being given that fact without any other information about n. Okay, let's think about other numbers. Maybe if I can find a small prime that does this. Oh yeah, so small primes like 11 or something. Thinking ahead, that's got last digit 1 and it's prime. See, I started to try and think about primes with 1 here, and then this would be a last digit 1. Is it true that no primes end in 1? No, 11 is prime. It has last digit 1, it has 1 prime factor exactly. That's an example where it is prime. So, okay, if you tell me that pi of n plus x of n is 2, then I can't tell if n is prime. It could be 10, it could be 11, it could be some other numbers, probably quite a few other numbers. This is true, I cannot tell, and not for lack of trying. Okay, how are we doing? We've got 3 left that might be false. There's this kind of nightmare scenario where I accidentally prove that all of them are true, and I've made a mistake somewhere and then I've got to find it. Let's keep working upwards. If pi of n is 1, so this means if you're prime, no, not if you're prime, if you're a power of a prime, if 1 prime factor, there are values of x of n which are impossible. Okay, so values of x of n which are impossible, I see, because if you have 1 prime factor, then you can make, this is, I think, saying maybe you can make some of the final digits using some n, but you can't make all of them. For example, pi of 2 is 1, right? Because 2 is prime, and it's got final digit 2. That's not really an example. That's an xn that I can make. I guess I can make 4 by looking at pi of 4. That's also 1 because it's just a power of 2. I've seen examples where pi is 1 here and the final digit's 8. I'm still interested in this multiples of 10 thing though. I think 10 is a good way into this problem because it's got final digit 0, and if your final digit is 0, then you're a multiple of 10, so you're a multiple of 2 and a multiple of 5. So if x of n is 0, then 2, 5 are both factors. So pi of n is bigger than or equal to 2. Okay, so there are values of xn which are impossible. 0 is one of the ones that's impossible. Maybe the others are all possible. Doesn't matter. This statement is true, so it's not the answer to this multiple choice question. Goodness, maybe I should have started at the top. Okay. Next one up. If pi of n is 1, so prime or power of a prime, there are some values of xn that mean n must be prime. Goodness, okay, so if I tell you that you're a power of a prime, and then could it be possible that I tell you the last digit and you say that's definitely a prime? It feels a bit unlikely because we have a lot of powers here, right? We have loads of powers of a prime. You know, instead of being a prime, it could be a power of a prime and still have pi of n being 1. Feels like in amongst that series of infinitely many powers of the prime, I might get some repeats of last digits. Do I believe that? I believe that a bit, I think. Let's have a think. So, if pi of n is 1, there are some values of xn that mean n must be prime. I can't immediately prove that one, which makes me suspicious that it might be false. We could prove it's false by thinking carefully about different values of xn. I'm actually going to move up to a and try and prove a to be true. If I can prove 4 of these to be true, then my answer to the multiple choice question is just going to be, oh, the other one's false. I can't prove it, and you told me that one of them was false. That's what I think is going to happen. Let's look at a. Maybe we'll get stuck on a as well. If pi of n is 1, so again that means 1 prime factor, there are some values of x of n that mean n cannot be prime. Yeah, okay, so 0, right? Oh no, because if xn is 0, then you can't have pi of n being 1. So if we're told that pi of n is 1, there are some values of xn that mean n cannot be prime. So can I think of a last digit that sometimes has x of n being sometimes has pi of n being 1, but means n cannot be prime? Yes, I can, because I was already thinking about 4. If xn given xn equals 4 final digit, there are no primes that end in 4. That's, I guess, a true fact, because numbers that end in 4 are even. There's only one even prime, and it's not 4. It doesn't end in 4. So, given xn is 4, it could be the case that pi of n is 1, but if you tell me that pi of n is 1 and xn is 4, then I know that you're not prime. This is true, which means it's not a. Which now really makes me think that b is false. If pi of n is 1, there are some values of xn that mean n must be prime. B is going to be my answer to this question. Let's quickly try and prove that that's false. So I guess to prove it's false, we'd think about the opposite. We'd say that for each value of x of n, n could be prime or it might not be prime. Okay, for each value of xn, for each xn, let's be precise. For each xn, there is an n with that x of n such that n is not prime. Okay, and that'll be an example for each xn that you can have n not being prime and still have pi n being 1, have xn be that last digit. Okay, I've got to think about each last digit. Okay, so 0 first, not 0 because you can't. If you're 0, then pi has to be bigger than or equal to 2, so I don't need to think about 0. If your last digit is 1, I need to think of a composite number with pi n is 1. I'm going to go for 121 because that's a power of 11. It's got pi n is 1, it's got last digit 1, it's not prime. Okay, so that shows that it's not the case that if xn is 1, then n must be prime. It could be 121. Okay, I need an example with last digit 2 that's a power of a prime but not a prime. I'm going to go with powers of a prime, and it ends in 2, so it's probably a power of 2, right? So I'm going to go with 32. That's an example which ends in 2. It's a power of 2, but it's not prime. For 3, I'm going to go with 7 cubed is 343. This is now testing my facts about powers of primes. I know that 2 squared is 4. I know that 5 cubed is 125. I could go 5 squared is 25. 6. If you end in 6, then you're... Oh no, if you end in 6, then you might be 16, which is a power of 2. 7. If you end in 7, you might be 27. That's got pi as 1, but it's not prime. If you end in 8, then you might be the number 8. That's got pi as 1, but it's not prime. If you end in 9, then you might be 729 or something, right? Which is 3 to some huge power. Or I could go with 9. You might be 9, which is 9 is a power of 3, so it's just a power of 3, so it's got pi of 9 is 1. Xn is 9, but it's not prime. and 0, you never have pi n equals 1. Example there, I suppose 10 doesn't even have pi n is 1, I suppose, so not 0. Okay, so this one is actually false. There are no values of x of n, which would mean that n has to be prime. You can find counterexamples for all of the last digits. Okay, my answer is definitely B. Okay. Okay, here we're given two functions a and b. We're asked to work out a of b of x and also b of a of x and show that they're equal. Off we go, I suppose. So a is 2 times thing plus 1, so that's going to be 2 times 3x plus 2 plus 1 over here, and that's equal to, I suppose, 6x, sorry, plus 4 plus 1 is 5. And over here, b of a of x means do a first, 2x plus 1, and then do b to that, which is 3 times 2x plus 1, plus 2, which is 6x plus 3 plus 2 is 5. So these things are both 6x plus 5. Okay, a of b of x is equal to b of a of x for all x. Okay, part 2. We're given n as a positive integer, and we're asked to work out a to the power of n of x, where a to the power of n of x means do a n times to x. So we'll do 2x plus 1, that's a1 of x, and then a2 of x is going to be 2 times 2x plus 1, which is 4x plus 3, just seeing if I can spot any patterns here. I'm going to work out a3 of x as well. That's going to be 2 times 4x plus 3 plus 1, which is 8x plus 6 plus 1 is 7. And okay, I can see a pattern emerging that every time I multiply by 2, the coefficient of x gets doubled. That makes sense because the coefficient of x goes through all of these doubling each time. And the constant seems to be 1 behind somehow. The constant is 1 less. Let's try and prove that. So if I do a n times to x, then I'm doing 2 times dot 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 times 2x plus 1 plus 1 plus 1 dot 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 plus 1 plus 1. What do I want? So this is n many 2's. A has been applied n times, so this is going to work out as 2 to the n x for that coefficient there, and then the other terms are going to be 2 to the n minus 1 plus 2 to the n minus 2 plus dot 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 plus 1, which is, that's a geometric series, exactly 2 to the n minus 1. Adding up that geometric series, which is what we spotted here, that this is 1 less than the coefficient of x. So this is my answer for a n of x. It's 2 to the n times x plus 2 to the n minus 1. Okay. The next part of this question defines f of x to be 108x plus c, where c is some positive integer. And we're told that that's been produced by repeatedly applying the functions a and b in some order. So someone has made f by applying a and b in some order. We want to know how many possible different ways there are, how many different orders for applying a and b there are to make f. Okay, so we've seen before that if we just apply a, we get these powers of 2. Every time we apply a, it doubles the coefficient at the front of x. When we apply b, so as a reminder, a is 2x plus 1, that's a of x, and b of x is 3x plus 2. When we apply b, it's going to triple the coefficient of x, multiply it by 3. So if we want to double sometimes and triple sometimes, how are we going to make 108? I think it's probably a good idea here to factorise 108, which is 2 times 54, 4 times 27, which is 2 squared times 3 cubed. So I think I want to do a twice, b 3 times. Okay, that's what I think has happened. Now, whenever I do that, I'm going to get a coefficient of 108 as my coefficient of x, so it doesn't matter what order we do them in. In fact, we saw before that A and B commute with each other, so it doesn't matter what order I do them in, I'll get the same answer for f, not just the x coefficient, but the same constant c as well. Now that I've decided to do A twice and B 3 times, there's only one possible f. That's relevant for the next part of this question. Okay, but this part of the question we're doing now says how many different orders are there that A and B could be applied. I want to do A twice, B 3 times, and the order doesn't matter in terms of making f. So all of these different orders of that are going to give me f of x precisely. So I'm applying 5 functions. 1, 2, 3, 4, 5, and I want 2 of them to be A, so there's going to be 5 choose 2, different notations are available, 5 choose 2 for how many different ways there are to do that. That is equal to the number 10. Yes. Okay. Right, part 4 asks us for the possible values of C, and by the logic that we just covered, there's only one possible value of C, because these A's and B's commute. So for example, A squared B cubed of x is going to be equal to A B cubed A of x, because we saw that AB was equal to BA for any input, so I can shuffle the A's and B's around, I can swap my A's and B's. Okay, that means we just need to work out, for example, what A squared B cubed is. Should we have a go at that? Let's have a go at that. Let's work out B cubed of x. So B of x is 3x plus 2, and I'm going to apply A squared to it afterwards. B squared of x is going to be 3 times 3x plus 2, which is 9x plus 6 plus 2 is 8. And B cubed of x is going to be 3 times 9x plus 8 plus 2, which is 27x plus 24, 26, and hang on a minute, these ones have also got, this constant is 1 less than the coefficient of x. Now I've got these powers of 3, but this has also got these coefficients being 1 less than x. What happens when I do a squared to this? So if I do a of 27x plus 26, then I'm doing 2 times 27x plus 26 plus 1, that's 54x plus 52 plus 1 is 53. That's interesting. So this has still got the coefficient of x being 1 more than the constant on the end there. Let's do 1 more a, so that's 2 times 54x plus 53 plus 1. That's 108, I've gone behind my face, sorry, 108x plus 107. So it's again 1 less than 108. So it looks like C has to be 107. That's what I get when I do B cubed and then A squared, and the order doesn't matter for the A's and B's. I always get the same function f. So C is going to be 107. But more interestingly, we've seen that it seems whatever I do, it seems like the constant is 1 less than the coefficient of x. Let's test that out. That's true for A and B, right? Because A has got this constant is 1 less. So if I just do A, then I get 2x plus 1. If I just do B, then I get 1 less over here. If I have some function of x, like kx plus k minus 1, and I apply a to that, what do I get? So I get 2 times kx plus k minus 1 plus 1. That's going to be 2kx plus 2k minus 2 plus 1 is 2k minus 1. So it's 2k minus 2 plus 1, 2k minus 1. So that's also got this property. So if it started with the property the constant is 1 less than the coefficient of x, then after I apply a, it's still got that property. The numbers are twice as big now, more or less, but I've got 2k and I've got 2k minus 1. What happens if I apply b to that function? So if I apply b instead, draw a line onto that, b of kx plus k minus 1 is going to be, well, it's going to be 3kx plus 3k minus 3 plus 2, which is 3kx plus 3k minus 1. So that again has constant term here, 3k minus 1, is 1 less than the coefficient of x. Which actually this means that whenever I do a or b, in any number of times in any order, I'm going to get something where the coefficient of x is 1 more than the constant on the end. It's not a coincidence that I've got 107, 108 in here. Okay, that's very powerful, and I'm going to use that to do the last part of the question. Okay, part 5. We're now asked for a very complicated thing. Are there positive integers m1, m2, m3 up to mk, and n1 up to nk for some k, I suppose? So, are there, let's break that down. Are there some sets of integers, and we're not told how many there are, there's the same number of m's and the same number of n's, but we're not told how many or what the integers are. What we want is a to the m1, b to the n1, x, plus, and then the sum of all of these things, adding all of these things up, is 214x plus 92 for all x. So is it the case that when we add these things together that we make by applying a and b a certain number of times, can we make this, I suppose, the same number of m's and the same number of n's so that each term in this series is defined? Can we apply a and b a different number of times maybe, add all of those things together and get 214x plus 92? Okay, we've already seen that if k equals 1, then no, because we've already seen that if you don't have all of these terms, if you just have this first one, if there's only one term in this series, a to the m1, b to the n1, we've seen that that first term has a constant that's 1 less than the x coefficient. So we could make 214x plus 213, or we could make 93x plus 92, but we couldn't make this thing with such a big difference between its x coefficient and its constant term. Okay, maybe if we added 2 of these together, we could make 214x plus 92, but actually that's not going to work either, is it? Because even if both of these have a difference of 1 between their x coefficient and their constant, then when you add them together, the difference is only going to be 2. Okay, so we must have lots of them, right? Using each of these a and b things, it's not enough to just have one term. That only gets you a difference of 1 between your x coefficient and your constant. We must have, how many do we want? So we must have, I suppose, 214 minus 92 terms in this sum, so that we can make that difference big enough. We're going to need to choose our a's and b's especially carefully as well, but if this is going to work, we're going to need to have a lot of terms. What is this number? I've been trying to work it out in my head. I think it's 122. 122 terms. That's a lot of terms. And I think that's a bit of a problem, right? So we could go and try some examples with 122 terms in, choosing the positive integers m1, m2, m122, n1, n2, n3 up to n122. Go and choose all of those terms and add them all up. But I think we're not going to get this function for all x, kind of because 122 is too many terms. I don't want to do any examples, but all of these terms, each term has a positive constant that's bigger than or equal to 1. A of x is 2x plus 1, b of x is 3x plus 2. These are positive integers, not 0, so we're going to apply some a's or b's. We're going to get a constant term that's at least 1, and we've got 122 terms. 122 is bigger than 92, so this is impossible. We can't make this function. On the one hand, the difference between the coefficients means that we'd need lots of terms, but on the other hand, once you've got lots of terms, the actual coefficients have to be quite big. So we can't make this particular function, no matter how many terms we throw in there, and no matter what we choose for the positive integers, m's and the n's. And that's the end of question 2. Okay, here's question 3. In this question, we're given a real number alpha. Well, we're not told what it is, but it's the same number throughout the question. And we say that a function is bilateral. Not a word I've heard before, but we say the function is bilateral if f of x is equal to f of 2 alpha minus x for all x. I'm already thinking back to question 1G where we talked about a reflection, and this seems a little bit like if you know your transformations of graphs. This looks like a reflection in the line x equals alpha, but let's pretend we don't know that for now. Let's do this question algebraically first. Okay, first part, show that f of x equals x minus alpha squared is a bilateral function. Okay, so I should plug in this is f of x we've been given, I should plug in f of 2 alpha minus x and work out that that is, I do the thing you plug in, minus alpha, so that's alpha minus x, and then you square it, and that is equal to, no matter what x or alpha is, x minus alpha squared. So that's equal to f of x, which is just what I wanted for this function to be bilateral. I've used the fact there that x squared is the same as minus x squared. Or I suppose u squared is the same as minus u in brackets squared. Right, okay. Okay, part 2. This is an example to show that this function is not bilateral. I suppose not all functions are symmetric in x equals alpha. Let's plug in f of, as we do, f of 2 alpha minus x. That is 2 alpha minus x minus alpha, which is alpha minus x. That is not the same as f of x, and I'm going to be really silly here and say compare coefficients. These are both polynomials and they have different coefficients, so these functions are not the same. I mean, obviously they're not the same. This is a line and this is minus the line. It's not the 0 line, I suppose. Okay, part 2. So we've shown that some things are bilateral, some things are not bilateral. Okay, part 3. If n is a non-negative integer and a and b are any real numbers, then we want to show that the integral from a to b of x to the n is minus the integral from b to a of x to the n dx. And you can think about this geometrically. You can think about this in terms of areas under curves, and you can argue about reflecting things. If you know about integration by substitution, then you could do a clever substitution here. That's all quite high-powered technology. We can do this integral. We can integrate x to the n. We get x to the n plus 1 over n plus 1 between b and a over here, which is b to the n plus 1 minus a to the n plus 1 over n plus 1. Whereas over on this side, when I do that integral from b to a, I'll get, well, this thing in entirety on the right-hand side. The right-hand side is minus, I'll put in the top limit minus the bottom limit, divided by n plus 1. And what do you know? These things are equal to each other because of this minus sign, which is going to save the day and flip around the top of that fraction. Okay, so these things are equal just because I can do these integrals. I don't need to think about areas unless I want to. Okay, part 4 is just to extend this and say, oh, if f is a polynomial, so what's a polynomial? It's a sum of some powers of x with some constant coefficients. So it's something like, I suppose, I don't want to use too much notation, but it's something like a0 plus a1x plus a2x squared plus like an x to the n. Okay. This thing we're asked to show here looks so similar to the previous part that I just want to use the previous part of the question, right? And then I can use the fact that this is x to the 0, I suppose. I want to use the fact that when I do this integral of f on the left, I can split that integral up to be a0 times the integral from a to b of x to the 0 plus a1 times the integral from a to b x to the 1 plus, and so on and so on and so on, up to the nth one. I could write this with a summation sign if I wanted to. Okay, I'm going to use the previous part to say each of these terms is minus the same thing but with the a and the b switched, and then combine them back together again and you get minus the integral of f of x dx. I've run out of space here. If I was writing this out in the test, I would put 2 more lines here to say flip each term, I'd write that out with the minus signs, combine them back together again, I would write out the right hand side. Okay, that's part 4. Okay, lots of parts to this question. Here's part 5. We're given f, any bilateral function. Remember, that's one with f of x is equal to f of 2 alpha minus x. And we're asked to consider the area under the graph of y equals f of x. Okay, so this integral on the left means integrating from alpha, sort of the line of symmetry, up to t. And this integral on the right says integrate from some other value up to alpha. So we're thinking about an integral using values just to the left of alpha and an integral using values just to the right of alpha. Earlier we talked about alpha being kind of this line of symmetry, so the function takes equal values on either side. That's really what this means. So it's perhaps not surprising that when you integrate a function, we're going to use the fact that it has equal values on each side. It's not surprising that we're going to get the same answer for these integrals. Okay, let's try and draw a picture. I'm going to try and draw something that looks like a general f of x. That's my general looking f of x. And you see it's got this line of symmetry about the point alpha, so that f of 2 alpha minus x is equal to f of x. F of x over here is going to be equal to f of 2 alpha minus x. I suppose I could rewrite this to say let x equal alpha plus u or something. Then this left hand side is f of alpha plus u, and the right hand side is f of, when you plug in x alpha plus u over here, you'll get alpha minus u. So this says alpha plus a bit gives you the same value of f as alpha minus a bit. Okay, so that's the kind of line of symmetry fact. Okay, here are the integrals. One of them is the integral from alpha up to t. T is bigger than or equal to alpha. So that's this area here on the left hand side of this equation, but the right hand side of this picture. And this one, 2 alpha minus t, is going to be, well, it's alpha minus, let's write that as alpha minus t minus alpha. So that's the same distance away from alpha, but on the other side. I'm being very careful, this is just what we want over here, say. Oh, not a great picture. 2 alpha minus t over here. Okay, and this area here is on the left hand side of the picture, but the right hand side of the equation, this is a reflection. And areas are preserved under reflection. It's, I suppose, a fancy way of saying that these areas are obviously equal by symmetry. So because these areas are equal, the integrals must be equal. Okay. We're going to define g to be the integral from alpha up to t of f of x with respect to x. Okay, so some new function g, it depends on t, which is this upper limit. This is the thing on the left over here, isn't it? Okay, so what are we going to do? We're asked to show that g of t is equal to minus g of 2 alpha minus t. Okay, so we want to show that g of t, that's the integral from alpha to t of f of x dx. This looks a lot like the previous part of the question, doesn't it? And we want to show that's equal to minus the integral g of 2 alpha minus t. Well, g of 2 alpha minus t means take this expression for g of t, and instead of plugging in t, plug in 2 alpha minus t. And that thing downstairs is f of x dx. Okay. So a bit of a wrinkle here. This is not the thing on the right hand side up here because the limits are the wrong way around. But we showed in part 4 that when you integrate a polynomial, f is any bilateral polynomial. When you integrate a polynomial, you can switch the limits if you put a minus sign in. So this is this minus f of x dx. That's because polynomial, and it's using the thing we found out in part 4. And then this thing here is equal to, so this thing I've written out is g of 2 alpha minus t. It's this integral, which is minus this integral, using the fact that f's a polynomial. And then using the fact that f is bilateral, we can use part 5 to say, aha, bilateral, part 5, to say, I recognise this integral now. This integral is the integral from, this is the integral from alpha up to t of f of x dx. And I've picked up a minus sign from the thing in part 4, which has followed me through, and I've now found that this is equal to minus, this is g of t. So I've shown that g of 2 alpha minus t is equal to minus g of t. I've got my minus sign on the other side of the equation. I guess I have to multiply through by minus 1 to get this thing in here. Okay, last part of this question tries to build on this to say, suppose f is a bilateral polynomial. So that means we can use this result from part 6. We know that g of t is equal to minus g of 2 alpha minus t. But we're also told that g is bilateral, which means that g of t is equal to g of 2 alpha minus t. I don't think you need to be a rocket scientist to add these equations together and say that, well, 2g of t is equal to 0. So g is 0 for all of its input values. This says g is 0 whatever input you give it, which they've written in the question as g of x is 0 for all x, or equivalently, doesn't matter what letter you use to make this statement, g of t is 0 for all t. It's the kind of language that I've shown that in. Either way, g is 0 for all x. Not very exciting function. Okay, that's question 3. Okay, this is a question about some circles. It's a geometry question. We're told that there's a circle of radius 1 and a circle of radius 3. The first part of this question is just about C1, so I'm going to try and draw that circle in. It is between this line L, which meets the origin at angle 2 alpha above the x-axis, and 2 alpha is less than pi over 2. This is back in the days when we used radians in the questions. Nowadays I think we'd say that alpha is less than 90 degrees, since not everybody has seen radians. Anyway, we're told that C1 is just touching both this line and the x-axis. So I need to try and draw a circle inside here that just touches both that line and the x-axis, and I've done that perfectly. Okay, we're asked to find the centre of this circle. Shall I draw some radii in? I want the centre of this circle and the equation of the circle, which feels like I know the radius of the circle, so once I've got the centre, I think I'm going to be okay to write down the equation. Okay, so this line, I'm going to draw in some radii. I really wanted to draw the radii in as soon as I drew the circle. These lines are both length 1, and I've got an angle over here of 2 alpha. I've got some right angles because these things are tangent, and this feels like the sort of GCSE geometry problem, I think, where you draw some lines in and you use the fact that you know some angles. So I think this is not so bad. This is an angle alpha. This line over here has length 1. I know that tan alpha would be the ratio of these two sides. So I think this side of the little triangle I've drawn has to have side length 1 over tan alpha. That gives me the coordinates for the centre now, because I now have the x coordinate. I already knew the y coordinate was 1. This is a circle of radius 1 that's just sitting on the x-axis, so its centre is going to be 1 up from the x-axis. The centre is going to be at 1 over tan alpha, comma 1. Okay, and the equation is going to be x minus the centre squared plus y minus the y coordinate of the centre squared is equal to the radius squared, which is 1. Okay, that's my circle C1. Next part of the question brings in the circle C2 as well, and wants to know when is it the case that C1 and C2 touch. So I need to go back to my sketch and put in C2 as well. So the C2 has radius 3, it's a bigger circle, and I'm interested in the case now, for part 3, where the big circle is just tangent to this smaller circle. Let's try and draw that. It's alright, there we go, okay. So that's going to go through here. I suppose I've got to think a little bit to say, well, these things are on a line, aren't they? This point of tangency. It's not off to one side or the other by symmetry, so I think this point of tangency is on that line somewhere. We've got some more radii to draw in here. I love drawing in radii on these pictures. Okay, that's 1, that's 3. Trying to do my lines nice and bold. Okay. And I've seen some problems like this before with tangent circles and things sitting on the line. The key idea I've seen before is to think about the two centres. I suppose we know where both of them are. We know where this one is. It's at 1 over tan alpha 1. I suppose this one is 3 times further away, right? Because it's still got like a similar triangle thing going on. But it's 3 times further away. We know where these points are in terms of alpha. Try and exploit that fact and draw on this diagram to maybe mark in the gradient of something or other. That's how I've seen these questions happen before. I'm going to draw in I've been thinking about the gradient of that line and thinking about how I know where these points are, so maybe I should use some sort of similar triangles thing on something involving both of these corners. I think I'm going to draw in this line and think about this triangle. I like right angled triangles. What do I know about this triangle? It's got angle alpha over here by similar triangles. This line I've drawn is parallel to the bottom line, so this is alpha. This thing over here looks like the bigger radius is 3, the little radius is 1. You wouldn't know it from my sketch, but this bit here is 2. So I've got a similar triangle. I know how big the similar triangle is. Oh, hang on, I know the hypotenuse of this triangle as well. It's 1 plus 3. That's 4. Okay, so I know quite a lot of facts about this triangle actually. I know that it's got an angle alpha over here. It's got side 2 over here. It's got side 4 over here. I think I can work out alpha now. Alpha is, hang on a minute, quite a famous angle, isn't it? That's 30 degrees. Yes, 30 degrees. So alpha is 30 degrees. Okay, just a quick check. 1, 2, root 3 triangle, 30 degrees at the top. Sure, okay. Part 4. For this value of alpha, where the circles touch, okay, so alpha is 30 degrees, a third circle, larger than the CT, we want to draw another, even bigger circle. It's drawn, it's going to be tangent to both lines and also touches C2. What's the radius of the bigger circle? So now we're thinking about alpha being 30 degrees. We've got our circle C2 from before, and we draw in a bigger circle C3. We still want everything to be tangent to both of these lines. Which it definitely is. This was 3, this is some unknown thing, and we're told that this is still 30 degrees. So this is alpha is the same alpha that it was before, 30 degrees. And it's tempting to go and do the algebra on this, right? To work out the radius of, this is tangent by the way, to work out the radius, do some maths over here to say this is x minus 3, this is x plus 3, to draw out this little triangle with side lengths x plus 3, x minus 3 and a 30 degree angle over there, and to sort of charge through like that, you'd write down, you see something like x minus 3 over x plus 3 is 1/2, and then you'd solve that equation to find out that 2x minus 6 was equal to x plus 3, so x must be equal to 9. You could go and do that, but instead of doing that maths, you could say, hang on, this is exactly part 3 set up, but 3 times bigger. Everything's 3 times bigger, right? Before, I had a circle of radius 1 and a circle of radius 3, and we found the angle was 30 degrees. Now I've just blown up the picture by a factor of 3, and I've been asked a different question about the picture, but it's the same picture, right? Circle, circle, tangent, 30 degrees there, bish bash bosh, the bigger circle is still 3 times as big. So it shouldn't be surprising that the sequence goes 1, 3, 9. The radii of these circles are in geometric progression by geometry. Okay, right, so the radius of circle 3 is 9. Last part of the question asks us to find the area of the region bounded by the x-axis and the circles C1 and C2. Let's have a quick look on the picture again. So that's this area over here. Let's pick a colour. Let's pick a colour. This area here between circle C1, circle C2 and the x-axis. So here that looks a bit like, to me, the area of this trapezium. I need to be careful, my diagram's quite bad. It looks a bit like the top is this horizontal line, but that's just badness of my sketch. There's a bit more here because there's still a gap. There's still a gap between the circles of that line. It's quite hard to tell what's supposed to be a gap and what's not. I've got to think of this, I think, in terms of, you know, the gap. The shape goes up to here, where it meets this line. So I could think of it, I suppose, as trapezium minus 2 bits of circle. Let's try and make that work. What am I going to need? I'm going to need all of the positions of all the points and all the distances between them, or something like that. Okay, seriously though, average 30 degrees, so this hypotenuse is 4, this is 2, I think this is 2 root 3 for the distance here, from this point to this point, 2 root 3. So the area of that trapezium area is going to be, what's the formula for the area of a trapezium? 1 plus 3 over 2 times 2 root 3, I think. A plus b times height divided by 2 is 4 root 3. That's the area of the trapezium, and then I need to do some subtraction. I need to subtract some percentage of a circle, right? Over here I've got 90 degrees plus 30 degrees is 120 degrees. So this bit of the circle is 1/3 of this circle over on the left. So there's a bit of C1 of 1/3 pi r squared is 1 over here. There's a bit of C2 as well. The bit of C2 has angle just 60 degrees, so it's just 1/6 of this circle. So that's going to have area 1/6 pi, and over there r squared is 3 squared, is 9. Okay, time to do some maths. I need to do 4 root 3 for my final answer. 4 root 3 minus 1/3 pi for the bit of C1 I'm taking off, minus 9/6 pi, simplify that, 3 over 2 pi. I think that's my final answer. I suppose I could simplify it one more step. 2/6 and 9/6 minus 11 pi over 6. Final answer for the area of that region. So this question asks us about a sum, and it's tricky because it's not a geometric progression. We know how to add those up. And it's not an arithmetic progression either. We know how to add those. But it's neither of those. It's not 2, 8 and then multiply by 4 again, and it's not 2, 8 and then add 6 again. It's not one of the series that we know about. Okay, so we don't have something from A-level knowledge of just how to do this sum or anything like that. In fact, it's the point of most of this question to work out a way to do this sum. Okay, here's what the question actually says. Let f of n be an plus b times 2 to the n plus c, where we're not told what a, b and c are, they're some constants. And suppose that, the sum is equal to f of n for all n bigger than or equal to 1. Okay, so that's saying that s1 is supposed to be equal to f of 1, s2 is supposed to be equal to f of 2, and so on, for all n. Okay, pretty powerful claim. We want to set n to 1, 2 and 3 to find equations that must be satisfied by a, b and c. Okay, so for example, let's try and turn this expression, s of 1 equals f of 1, let's try and understand both parts of that equation. So s1 means the sum of, I think, the terms up to 1 times 2 to the 1, which is, oh I see, just 2. So s1 is 2, and s2 is going to be, I think, the sum of the first 2 terms. 2 plus 8 is 10. S3 is going to be 2 plus 8 plus 24, which is 34, I think. And then, on the other hand, we know what f is as well. F involves a, b and c. So this is how we're going to get equations for a, b and c. Have I left enough space for this? Maybe, maybe not. Okay, f of 1 is, I'm going to plug 1 into this expression, and I'm going to get a plus b times 2 plus c. Okay, so this is a plus b, I'll say it out loud, a plus b times 2 plus c. Okay, that's one of my equations. I'll write it over here as well, because that's going to be important. 2 is a plus b times 2 plus c. Okay, and let's do the one for S2 as well. So that comes from plugging in 2 into this expression. So that's going to be 2a plus b times 4 plus c. And then my third equation is going to come from plugging in 3. It's going to give me S3 is f of 3, which is 3 times a plus b times 8 plus c. Okay, and to nobody's surprise, the next part of the question is going to ask us to solve these simultaneous equations for a, b, and c. Okay, so part 2, solve the equations from part 1 to obtain values for a, b, and c. There's a strategy here, I suppose, to solving these simultaneous equations. We get to decide what we're going to eliminate each time. They all involve a plus c, so I think I'd like to do differences of these equations just to get rid of the c's. That feels like progress. If I do that, then I'll get, well, this is 8a's over here, take away 2a's is 6a's, 4b's take away 2b's is 2b's, and I'll get rid of the c's. And if I do the difference of the second and third equations, then I'll get 24 is 24a minus 8a is 16a plus 8b's and 4b, if I take 4b's is 4b. Okay, right, great. So I found the difference of the first two and the difference of the second and third. I could have done the difference of the first and third. I didn't feel like doing that. Maybe that's easier, you tell me. Okay, it wouldn't give me a third different equation from these two. It would be the sum of these two equations. Okay, so not an independent conclusion without C. Okay, now I've got these two equations. I've had enough time to think. I'm going to do the second of these minus twice the first, because I can see that's going to get rid of the b's. So 16a minus 12a is 4a. Yes, because I'm taking off twice this one. So a is 2, and now I can go back up again and work out that b has to be 12 take away, I want to do 12 take away 4, so b better be minus 2, I think, and c should be, well, if I go all the way back up here, then I've got a plus b is minus 2, 2 times 2, 0 times 2 is 0, so I need c to be 2. Quick check, so if I plug these in, I get 0 times 2 plus 2, I just did that one. 2a plus b is 4 take away 2, it's 2 times 4 is 8, plus that 2 is 10, looking good. Last check, 3 times 2 is 6, take away 2 is 4, multiply by 8 is 32, add on that 2, 34. Those values of a, b and c satisfy these three equations. Okay, 2 minus 2, 2. Okay, part 3 says something different. It says using these values of a, b and c, show that if it's true that sk is equal to f of k for some k bigger than or equal to 1, then sk plus 1 is equal to f of k plus 1. Okay, so if you've seen proof by induction, then you might recognise this as the inductive step of a proof by induction type argument. If you haven't seen proof by induction, then don't worry about that. This isn't actually going to ask us to do proof by induction. This is just going to ask us to check this fact, which we can engage with even if we don't know about proof by induction. Okay, this is saying if sk is equal to fk, so I want to write down that fact because that seems like an important fact. Sk equals fk, so let's write down some maths. This is true if sk is equal to ak plus b times 2 to the k plus c. And now I've remembered that they told me to use these values of a, b and c, I think. So that would be 2k minus 2 times 2k plus 2. Okay, so that would be the value of sk. And then the question asks me to say something about sk plus 1 in terms of f of k plus 1. Show those things are equal. What have I got? I know that sk is this, and I suppose I know what sk is. It's the sum up to k 2 to the k. So then I suppose sk plus 1, the only way I know it's related to sk is that it's pretty much the same sum, but with an extra term on the end. That's what these dots mean. I think that these dots mean that you keep going until you get up to the nth term to find Sn. So here, for my sk thing, I'll have k terms. Sk plus 1 is going to be the same, but go one term further to add on one extra thing. Okay, so in fact I can make that concrete. I can write then sk plus 1 will be sk plus just one more term in this sum. Okay, which is, now I'm going to use the fact that sk is f of k. I'm going to use this expression for s of k. I guess I'm just used to taking expressions, plugging them into expressions to try and combine facts together. A bit like how when we're solving those simultaneous equations, I'm used to writing down particular things. I can already see that this is looking just about fine. Right, okay, what have I got? I'm going to bring together some factors of 2 to the k, I think. So, what am I expecting, by the way? I'm expecting fk plus 1, so I'm expecting something with a 2 to the k plus 1. You know, I sort of believe that this is true. The question's telling me to do it. So I'm expecting something with a 2 to the k plus 1 in here. I've got a 2 to the k plus 1 over here. Over here, this looks a bit like a 2 to the k plus 1 if I pull out a factor of 2. I'm running out of space there, but I think I've made my point that I can write this in terms of 2 to the k plus 1 as well. And now this is looking almost correct. Almost right. Wow, so when I add these things together, what do I actually get? I'm going to get 2k, 2 to the k plus 1, plus 2. Okay. New question, is that what I wanted? I suppose I should check what f of k plus 1 is equal to. I need to do that somewhere else. I'm going to do that over here. Sorry, it's all getting a bit squashed together. I need to check that f of k plus 1, is it equal to this thing at the bottom? Well, f of k plus 1 is 2 times k plus 1 minus 2, that's this bit, an plus b, times 2 to the k plus 1 plus c is 2. Okay, so that's 2k plus 2 minus 2. Aha, great news, this is 2k inside these square brackets here, times 2 to the k plus 1 plus 2, which is then equal to this. So my conclusion is, hooray, great news, this expression, which is f of k plus 1, is equal to this expression, which is s of k plus 1. So I've shown that those two things are equal. Okay, I got a little bit scared of the algebra in the middle there, but it's all worked out. The next part of the question says that we can now assume that Sn is equal to f of n for all n bigger than or equal to 1. If you've seen proof by induction, you'll know that we should check a base case and then use inductive reasoning to say, hey, we've proved this for all natural numbers n bigger than or equal to 1. We should write out that stuff at the end of our proof. We're not asked to prove this by proof by induction. We're not asked to know about proof by induction. We're just told we can now assume that Sn is equal to f of n for all n bigger than or equal to 1. I'm going to write down that statement that says that 2 plus 8 plus 24 plus ... plus n2 to the n, that's s of n, is equal to, we're now allowed to use this fact plus 2, using my values of a, b and c from before. Okay, and part 4 tries to build on that idea and say, can you work out these sums? So this one is n plus 2 times n minus 1 plus 4 times n minus 2 plus 8 times n minus 3. So it's sort of powers of 2 and this time decreasing values of n. So I guess it's sort of related. Well, it looks kind of similar. That before we had increasing numbers. This is sort of 1 times 2. This was 2 times 2 squared. This was 3 times 2 cubed, and so on up to n times 2 to the n. And now we've got the numbers the other way round. I can't immediately see a way into that. But the next one looks more friendly to me, because that looks like instead of having 2 to the n, we've got 2 to the minus n. Is that useful? Oh, I think this one is, hang on, if I write in this term here, so the term before will be n minus 1 over 2 to the n minus 1, that to me looks like, you know, this one, this last term here, is n over 2 to the n, looks like this thing divided by 2 to the n, and this previous one has kind of gained a factor of 2, but then changed the n to an n minus 1. I think this one, in fact, looking term by term, if you wrote it in the other order, so if you wrote it in the other order, n over 2 to the n plus n minus 1 over 2 to the n minus 1 plus ... plus, and then this last one is going to be 1 over 2. I think un is just going to be equal to Tn over 2 to the n. I think, yeah, okay, dividing each term by 2 to the n, and then all the powers of 2 just work out. Okay, so I haven't worked out Tn yet, but I've spotted that Un is just going to be kind of small bit of question, it's just Tn divided by 2 to the n. Okay, so maybe that part's easy, and I need to put all my effort into working out Tn. Okay, so what do I know? I know how to do a couple of sums now. I suppose I want to use the previous part of the question. I could go and do the work again. I could say, well, maybe this has a similar form with different values of a, b, and c, and I could go and say, well, maybe Tn is equal to an plus b 2 to the n plus c with different values of a. Maybe these are a prime, b prime, c prime for new values of a, b, and c. That's actually quite a lot of work, but I think it does work. That gives you some rule for T of n. I guess I'd probably want to prove it by induction at that point to prove that it was true. How else can I use this previous fact? So I really want to find a 2, 8, 24 in this problem, in this Tn thing, so that I can just be lazy and use the previous part of the question. And I suppose there's a 24 hiding in here, in this 8 minus 3. I've got 3 times 8 here. I wonder if I can make that work. So I guess that 4 times 2 is 8. 2 times 1 is 2. So maybe if I multiply out all the brackets in Tn, I get something nice. I'll have to think about that. Okay, so I'm going to get Tn is equal to n plus, I haven't had any ideas about that yet, 2n minus 2 plus 4n minus 8 plus 8n minus 24. Let me see, I've had this idea because I've spotted this minus 2, minus 8, minus 24 pattern. How does this end? So this will end with, I guess I'm thinking of this 1 as being n minus 1. So this will end with plus, and then it's, what is it? It's 2 to the n minus 1 times n minus, this is a little bit silly, 2 to the n minus 1 times n minus 1, I think. Okay, so what have I got? I've got, here, I've got some minus terms. The minus terms look almost exactly like s of n, but maybe not going up to the same n 2 to the n. And the positive terms, n, 2n, 4n, 8n, they look quite nice. That is a geometric series. They all involve n, and there's a common ratio of 2. So here's my strategy. I'm going to add together the terms that have n in here, these ones, multiples of n, using some geometric sum, and then I'm going to subtract sk minus 1, or sn minus 1, I think. I don't quite want all the s's. Okay, let's try and do that. So I've got 1n, 2n's, 4n's, 8n's up to 2 to the n minus 1 n's. That is 2n minus 2 to the n minus 1 n's, using a geometric sum. And then I'm going to minus sn minus 1. Let's just make it really clear what I'm doing. That's 2n minus 1 n minus, I need to use my previous formula, which was an plus b times 2 to the k or n or whatever, 2 to the a plus 2. All of that was my formula for Sn. Okay, I can probably simplify that a bit. In fact, I can already see there's going to be a 2 to the n, or maybe not a 2 to the n that might cancel out of that. Who can say? But yeah, that probably simplifies down a little bit. But that's my formula for Tn. And then my formula for Un is going to be that divided by 2 to the n. A little bit of work for you to check your answer against what I've written. You might have a different equivalent expression, and maybe you had a different method as well. Maybe you did go and try this an plus b 2 to the n plus c for new values of a, b, and c. Okay, so that's my work for Tn and Un, and I haven't simplified my answer. I suppose it does say simplified expressions. How much do I want to simplify? No, I'm not going to simplify it anymore. Right, okay, homework. Okay, part 5. We're asked to find the sum from 1 to n of sk, which is sort of the sum of some sums, which is a bit bit much really. But luckily we've already found a formula for SK. I said before that I like plugging in formulas whenever I know a formula. Here we've worked out that this is 2k minus 2, 2 to the k plus 2. I'm going to do that sum. Okay, from k is 1 up to n. And to start off with, I've got basically no ideas. I can do this last bit. This last bit's 2 for each of the terms. And I've got n of them. So when I add up n2s, I'm going to get 2 times n. So that bit I'm okay with. What else have I got? I've got minus 2 times 2 to the k. These terms in here, these look like just powers of 2 for each powers of 2 for each k. As I change k, I'll get power of 2 times 2. That looks all right. I reckon I can do that. I'm going to have to do a geometric sum. And then this term over here looks like k2 to the k. I don't know how to do those. That's going to get a wobbly face. Right, okay. Off we go. Let's try and do some of these sums. Or not do the sums that I can't do. What have I got? So this first term here is 2k times 2 to the k minus 2 to the k plus 1 plus, and then I suppose we'll do that sum and then I will add up n lots of 2 to get 2n. Okay. Right, I still need to do that geometric sum I said I'd do. I suppose it's twice. What does it start at? It starts at, when k is 1, this starts at 2 to the 2, which is 4. So there's a minus sign, but other than the minus sign, it's 4 plus 8 plus dot 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 plus 2 to the n plus 1. When k is n, we'll put n in. Okay, so that is 4 times the sum from 1 to 2 to the n minus 1, so that's 4 times the sum. Sorry, I know my geometric sum starting at 1. I haven't memorised the formula. So that's going to be 2 to the n minus 1, right? Take off the 4, divide by 4, something like that. Okay. Yeah, something like that. I should be more confident than that. Something like that. Okay, so that's that bit of sum. And I still need to do this sum, 2k, 2 to the k. I've done that geometric sum now, and I've got my n lots of 2 over there as well. They've been very nice all the way through. Okay, so one last bit of sum to do, and after staring this for a bit, I remember that this whole question is about doing sums like k, 2 to the k. Those are the things that we were adding up when we worked out sk. So this bit over here, I mean there's a 2 out the front as well. Every term's being doubled, but you can't trick me. This is just 2 times Sn. And then there are the other bits and pieces as well. Okay, so I'm going to plug in my formula for Sn one last time in this question, and then I'll have a nice expression. It's recognising that this sum of k2 to the k is exactly what sk was, exactly what Sn was, right back at the start of this question. Okay, final step is to plug in my expression for Sn, which is going to be, I've written this out so many times now, 2n, 2 to the n, I'm doubling it, so let's put that 4 minus 4, 2n minus 1 plus 2n. Okay, that's my expression for this sum. Shall we simplify this one? No. There you go. Okay, here's a fun question. This is about people doing a dance. There's 4 of them. They're holding hands in this pattern, and they're each going to be assigned a number, 1 or 0, which is something to do with dancing. So maybe there's some numbers 1, 0, 0, 1. Okay. This question written by computer scientists. Each dancer is assigned a 1 or a 0 to determine their steps. There's always at least 1 1 and at least 1 0 in the group of dancers. They can't all be the same. And a dancer is said to be offbeat if their assigned number plus the numbers assigned to the people holding hands with them is odd. So in my example, this person here is offbeat because 1 plus 0 plus 0 is 1. This person, those add up to 2, so they're not offbeat. Do we call that on beat? I can't say, no idea. Here, this person looks like they're not off beat as well. I'm getting confused already. And this person, there's a 1 here, a 0, and a 0. So this person is off beat. Okay, but it's about adding up them plus the people they're holding hands with. All of those numbers. Okay, whether that's odd or not. Okay, so this is not an offbeat dance because some of my dancers are not offbeat. The question is, how many ways are there for 4 dancers to perform an offbeat dance? Explain your answer. Okay, so we've got to think about what would happen to give everyone an odd total. So I suppose their totals might be 1 or they might be 3. Those are the possible odd numbers that they could be. They're adding up 3 small numbers, right? So their totals could either be 1 or 3. Okay. Let's think about some cases. Let's say maybe there is a dancer. Maybe A has total 3. If A has total 3, then I can see that A is a 1, and C and B are both 1 as well. That's how you make 3. But then I would look at B and I'd say B so far has sum 2. B needs to have an odd total. B is currently 2. So it looks like D has to be 1 as well, so that we can get B up to an odd number. But then there's a problem. Because now everyone is 1. And we're not allowed to have everyone 1. There must be a 0. Okay, so not this. A does not have a total of 3. Okay, feel like we're making progress. Similarly, I suppose this picture's kind of symmetric, left and right and up and down. So B's not 3 either, and C doesn't have total 3 either, and neither does D. So they must all have total 1. Total 1. Okay. How can I do that? So at least one of them is 1. Let's say one of them is 1. So maybe A is 1 instead. I know there is at least 1. Say A is 1. There is a 1. Why not A? They're kind of all in similar positions here if you flip the picture around symmetrically. Let's say A is 1, and if they've all got total 1, then B and C must be 0. Okay, so I suppose B's total is currently 1 from A, so D is 0 as well. Is that alright? So C looks like their total is 1, adding up A and C and D. And D, oh dear, D has 0, 0 and 0, so that's not okay either, because now D is not offbeat. So I think I've reached a problem again. I think there are no possible ways for 4 dancers in this pattern to perform an offbeat dance. I think 0 is the answer to how many ways there are, because if all the sums were odd, then either the sums are either 1 or 3. If a sum is 3, then look at the dancers. The dancers there are 1. That one and their neighbours are 1. The other dancer must be 1 to get the total up to an odd, but now everyone's 1. If, on the other hand, nobody is 3, everyone is 1, then find me a dancer with the number 1, look at their 2 neighbours, and say, well, hang on, those are both 0, and the other one also has to be 0, so that those neighbours have the right total, but now that last left out one on the other side, that's total 0. Okay, that was all of that in words. Right, okay, part 1, no ways to do that. Okay. Part 2 introduces a new dance with 6 people standing in a hexagon. And the question says, how many ways can this ring of 6 people perform an offbeat dance? Okay, so there's sort of rotational symmetry here, and at least one of them has a 1. Let's start by saying, So we'll have to think, whenever we get a solution, we'll have sort of rotations of that solution as well. But let's start by saying, suppose A is 1 at the top. Now what? Okay, if, so this is A, B, C, D, E, F. Okay, if, okay, so B and F, I'm thinking about A's total here. B and F are supposed to either both be 0 or both be 1, I think, so that the total for A, of A's own number plus the ones they're holding hands with, is odd. I'm trying to make an offbeat dance. So I think either B, F, both 0 or both 1. If B and F are both 1, that was a problem before. We showed that everything was 1, doing something like this. I think I'd now look at B. Look at B. That says that, hang on, B currently has 1 plus 1. That's 2. Welcome to the Matt live stream. But we're going to need C as well. We're going to need C to bring up B's total to 3. So C must be 1. Now look at C. And keep going round. C currently has a total of 2, so it needs another 1. D currently has a total of 2, so it needs another 1. Oh dear, everyone is 1. We're not allowed to have all the dancers on the same number. Okay, so not that. Let's try having B and F both be 0. Okay, so if I take B and F, so this is our problem. Okay, so let's take B and F both being 0. If I do that, then look at B. Its sum is currently 1, so I don't want C to be 1 as well. Otherwise, B's total will go up to 2. I want C to be 0. Similarly, around this side, I want E to be 0. And now if I look at C, I've got 0, 0, so I want D to be 1. No choices here. I want D to be 1 so that C's total is odd. Deep breath, look at D. D's total is now also 1. Okay, so everything is good. This is an example. For example, this, and this is, I think, the only possibility if A is going to be 1. Of course, we could take this solution and rotate it around to find solutions where B is 1, or find solutions where C is 1. One of them's got to be 1, so we've got to start somewhere, but we've shown that once you put a 1 down, you have to put 0, 0 as the neighbours, and then work your way around 0, 0 for those ones, and 1 for the opposite person. So we can change the letters by rotating everyone, but we can't change the pattern overall. Okay, so we must have, so it turns out you must have opposite pair 1. There are 3 ways to do that, because there are 3 different opposite pairs who could be the ones. A and D, B and E, or C and F. Rotate. Okay, that's part 2. Part 3. In a ring of n dancers, explain why an offbeat dance can only occur if n is a multiple of 3. So now I'm supposed to imagine a lot of dancers, or at least some. I suppose it's the next part of the question that says n bigger than 4. But if I imagine a lot of dancers, I suppose I want to use a similar argument. You see, we saw that 6 is a multiple of 3, and we saw it was possible in that case. Okay, so let's try putting in at least one of the dancers is 1. So let's find a dancer with 1, and now count around. We've seen if both of their neighbours are 1, then you can do this thing working around. We saw before that leads to everyone being 1. Keep working around the circle. So their neighbours are both 0. Okay. Now look at the neighbour. The sum is currently 1, so we want the next neighbour to be 0, so that this person works. And then we want this person to be, the sum is currently 0, so we want a 1. And now we're back to having a 1 with a 0 on one side, so this pattern is going to repeat. What do we want? Well, this pattern repeats around the circle. Every 3 people along is a 1, so we must have we must get back to where we started. Where we started was having this person as a 1 after doing a multiple of 3 steps around the circle. Every third person is a 1, so that when we get back around to here, we have 1, 0, 0, 1 around the end. So this is like dot, dot, dot around this side. Not just one person here, like 2 people. Okay, there's some extra people here. Okay, so n must be a multiple of 3. N, the number of people, must be a multiple of 3 so that we can fit that pattern neatly into the circle, like we did over here. Every third person is a 1. Part 4. Now we've got a dance where people aren't holding hands with the nearest dancer, they're holding hands with the dancer 1 away from them. So, example with n is 5, they're not in a ring, they're in, this person's holding hands with this person, this person's holding hands with this person, this person's holding hands with this person, and this person. Okay, for what values of n can the dance be offbeat? Okay, so I suppose this one I should look for a dancer who's 1, and then look at, I suppose previously we were looking at their neighbours, now we're looking at people they're holding hands with, which is not quite neighbours. Those are both 0. I should work my, or neighbours, those are both 0, and I should work my way around this pattern. So instead of going around the circle, I should follow the pattern. When n is 5, that forms a new sort of loop. It's not going around the outside, but it kind of cycles around like that, doesn't it? So if I skip a person each time, then I don't get back to where I started. The first time I draw around the circle, I go yoop, and then over here I put a 0 in, and I go over here and I put a 1 in, because I need every third person following this pattern to be a 1. It's kind of the same pattern. The topology is different, but the people are in different places, but I'm following around the same pattern. I think I still want n to be a multiple of 3, and it's not if n is 5. Let's look at that a bit more, because it's not obvious to me that when n is bigger I'll always get something like that. If n is 6, what happens? So if n is 6, then when I skip every other person, I do get back to where I started, like this, you see. And I get this kind of shape like that. Now I've kind of got 2 separate loops going on. So here I've got n even, n is 6. I get 2 loops going on. And I suppose I want each of those, what do I want? I want each of those to be, I want everyone to be offbeat, so I want both of those loops to be offbeat. So I want n over 2 to be a multiple, half of them to be a multiple of 3. Okay, when n is odd, I think I get a picture like this. I get some sort of 7-pointed star or 9-pointed star of how this pattern joins up. When n is even, I think it splits into 2 loops. Okay, so in this case I want n to be a multiple of 3, and in this case when n is even I want n over 2 to be a multiple of 3. Which values of n is that? Well, it's the odd multiples of 3. These are the odd multiples of 3. And this is even, are these multiples of 6 or something? When you divide by 2, they've got a factor of 3, because when you divide by 2, it's an even number, you divide it by 2, you've still got a factor of 3, so these are even multiples of 3. Okay, right, so I've got the odd multiples of 3 and the even multiples of 3. I think I still want, overall, I still want n to be a multiple of 3. That's still all of the cases where this works, even though sometimes now it splits into 2 loops, sometimes it's just 1 loop, topologically equivalent, but I still want n to be a multiple of 3. The next part of the question brings us to an alien planet where the aliens have 3 arms, and asks us about 4 aliens doing a dance. Some things are constant. The aliens like to dance in the same way that we do, or computer scientists do anyway, which is to have people holding hands and assigned 0 or 1, so that the sum of them plus everyone they're holding hands with is an odd number. That's an offbeat dance. So here the aliens are holding hands, have I got this right? 3 arms, they're holding hands with each other, each holding hands with each other. Right, okay, so everyone's holding hands with everyone. You can do that with 4 aliens. how many ways can they perform an offbeat dance? Okay, so I want all of them to be an odd sum. Hang on, aren't all of them going to be, when they work out the sum, each of them is going to work out the sum, each total is going to be the sum of all 4. So I want the total, I'm fine so long as the total is odd. So I want the total, I want that total. You know, before they were just looking at themselves plus the 2 people they're holding hands with. These aliens in this square are looking at every other alien and themselves. So they'll each be happy if the total is odd. I suppose it could be 1 or 3. How many ways can we do this? We could have one of them be a 1, like this, or we could rotate that picture, or we could have 3 of them be a 1. And rotate that picture. Does that work? Their sum is still odd. All of them see an odd thing. Yeah, okay. So I get 8 ways to do that. Yes. 4 aliens dance, each holding hands with each other. Yes, okay. Is it a bit debatable whether these are different? No, this is fine. So long as we can tell the aliens apart, then we're going to be able to say, you're the one who's won, this is a different dance because you're now on the beat and the other 3 are off beat, or the other way around. Okay. Confusing these aliens, right? Part 6 has 6 aliens standing in a hexagon, performing a new dance. They're holding hands in this pattern, hexagon, holding hands with the opposite alien, like this. There we go, drawing skills. Right, okay, these ones are holding hands opposite. How many ways can they perform an offbeat dance? Okay, so now the aliens are looking at the sum of their own number plus 3 more numbers, the 2 neighbours plus the one opposite them. I suppose that sum could still be 1 or 3. What do I want here? I suppose I could start by thinking about, before we had some success, by thinking about what happens if one of the sums is 3. And sometimes we started by saying, find me a dancer with 1, and looking at that dancer. I'm trying to decide which is the best start here. Let's try the second one. Let's say find an alien. There's rotational symmetry again. So find an alien that has 1. Put it at the top. We'll have to remember afterwards that we can rotate this picture back again. Now it might be the case that all of its neighbours are 0, or it might be the case that 2 of its neighbours are 1. 2 of the aliens it's holding hands with are 1. What do I want to do here? Okay, I could check a lot of cases. I just don't want to make a mess of this. If all of its neighbours are 0, maybe all neighbours 0. If all of its neighbours are 0, then I could look over. I could look at its the one over here. I'm getting a lot of cases already. I could look over here and I could say, well, this one is a 0 at the moment. It's got a 1 opposite, and then 2 more, so it can add up to 1 or 3. To make 3, it would need a 1 and a 1 over here. Okay, so I'll remember this pattern. Does this work? Okay, so this is one possibility, I think, because this is going to be 1 plus 0 plus 0 plus 0 is 1. This one's going to be 0 plus 1 plus 1 plus 1 is 3. And this is going to be 1 plus 0 plus 0 plus 0 is 1. Okay, so this is good. This is a solution. I don't think it's the only solution. Okay, what other cases did I have? So backtrack a bit. We put a 1 in here and a 0 in here, and then found that 1 in here, a 0 in here, 0, 0. I put a lot of numbers in, and then tried to work out what was implied by that. What else can we do? Let's draw a new picture. So we could think about, again, having a 1 up here. One of them's got to be 1. And think about having all 3 of these 0 again. I was also considering what would happen if these 2 were 0. That's another way that the dancer down here could be offbeat. I think this picture doesn't work because I think this 0 here is connected to too many zeros. So this sum here is 0. So this is not okay. So I've seen if I put a 1 at the top and 3 zeros in like that, then I get 1 at the top and 3 zeros like that, then I get some 0. I must put these 1s in over here. I can't have zeros. Okay, that feels good. So I suppose maybe I could think about, do I always have something like this with a 1 and 3 zeros in? Maybe not. Maybe maybe I have. Maybe I don't have some 1 at the top where my 1 that's 1. Can I have one that's? It is 1 and its sum is 3. So this is the other case. Maybe all neighbours 0, or maybe 2 neighbours 1. 1 is 0. Feels like a lot of cases. Let's hope that it works out to not be too bad. Okay, so maybe that's 1, 0, 1. I suppose there's 2 cases to consider. Not a lot of cases, 2 cases to consider. Either one of the side ones nearby is 0, or the one opposite is 0. Okay, there's a reflection of this picture too. Maybe that gives me more solutions. I'll remember that later. Reflections and rotations. Okay, check both of these. So here, what have I got? I've got 1, 2 at the moment, so I need one of these to be 1 and the other to be 0. And over here, this is 1, 2 at the moment, so I need one of these to be 1 and the other to be 0. Whereas if I look down here, then the sum is currently 1, so I need both of these to be 1, or both of these to be 0, so that the sum works out for the bottom one. So this is a problem. This is not okay. Thinking about this alien down here, it's asking these 2 leftover ones to add up to an even number, so that this 1 more makes odd. And this alien over here is asking the 2 leftover aliens to add up to an odd number, so those 2 aliens plus 2 is odd. Problem. What about in this picture? I'm hoping that this leads to problem as well, actually, I think. And this is my last case to check. Okay, so I've got 2 aliens left over. This alien over here is saying, well, I've got a sum of 2 so far, so I'd like the remaining sum to be odd. And this 0 over here is saying, I've got a sum of 1 so far, and I'd like the sum of these remaining 2 ones to be even, so that the sum of all 4, me and top 1 and these 2, is odd. This is a problem as well. Okay, so I checked lots of cases. I've now checked all of the possibilities. Maybe find me an alien that has 1, maybe all its neighbours are 0, in which case you've only got a couple of possibilities left for those other 2 aliens, and only one of them works. Or maybe one of its neighbours is 0 and the other 2 are 1. In that case, nothing works. So I've got this picture, plus rotations and reflections I thought about at some point, but actually there's only one interesting other alternative, right? You can rotate it by 1 step, and that gives you swaps all the 1s and 0s. So I found 2 ways, and I'm pretty sure I haven't missed any ways. That's my answer for part 6. Okay, it's got really dark now. Here's question 7. It's about an n fan, which consists of a row of n points called the tips that are in a straight line together with another point called the hub. So this is the hub. These are the tips over here. The n tips are joined to each other and to the hub with line segments. For example, the left-hand picture here shows a 1, 2, 3, 4, 5, 6. This is a 6 fan. Okay, so that's 6 fan, looks a bit like a fan, lots of lines joining up, 7 points. Okay, for a given n fan, an n span is a subset containing all n plus 1 points and exactly n of the line segments, chosen such that all the points are connected together and there's a unique path between any 2 points. This is a 6 span obtained from that 6 fan In this 6-span, the tips are in groups of 3, 1 and 2, with the top group containing 3 tips. Okay, right, so there's a 6-span. I've got n line segments to use, so I suppose every time I draw a line segment, I need to add in another point. I need to get, I start with the hub, and every time I draw a line, I'm adding on connecting in one extra point. So it's sort of only just possible, I suppose. No extra wasted lines. I suppose that was what they mean by unique path. No, kind of loops around. Got to reach everything. Okay. Part 1 wants us to draw all of the 2-spans, all 3 possible 2-spans. So a 2-span would come from a 2-fan. Let's draw a 2-fan. Okay. And then the challenge, here's the hub. The challenge is to find 2 lines out of that, so all 3 points, but only 2 of the line segments, so that everything's connected together. Okay, so there's 3 possibilities for which line I don't use, and because there's 3 in total, I think those are going to be the 3 possibilities, right? I could not have that line, or I could not have that line, or I could not have the top line. Okay, those are my 3 2-spans. Okay, connect to the top, connect to the bottom, or connect to both. Those are 2 lines and 3 points. Okay, part 2 asks me for 3 spans. Okay, so a 3-span would come from a 3-fan. Let's draw a 3-fan very quickly over here. So a 3-fan would have 3 points connected to each other and all joined to the hub. And then a 3-span would be 4 lines, so that everything's connected. I think I'd like to break this down into cases to think about whether the hub has 3 lines coming out, or 2 lines coming out, or 1 line coming out in my 3-span. So let's think about if I've got 3 lines coming out of my hub, then I'm done. That's my n lines. So that's a 3-span. If I've got 2 lines coming out of the hub, well, I could connect to the top and the second one, but not the third. Or I could connect to the outside ones, but not the middle one. Or I could connect to the bottom 2, but not the top one. And then in each case, I've got 1 line left over, and I need to join everything up. So here, I've got 1 line left over, and I need to join this up. I can't join to the hub, otherwise I've got 3 things coming to the hub. So I need to join this, I suppose, to here. Similarly, in this case, I need to join to here. In this case, I suppose there's 2 possibilities. I could join this one up, or I could join it down. Okay, so those are the cases with 2 lines coming out of the hub. Then cases with 1 line coming out of the hub. If I go up, then I've got 2 lines left to connect to these points, and nothing more to the hub, so I'm going to have to join both of those things in. If I go to the middle, then I've got 2 lines left, and I can't put anything else to the hub, so I'll do that. And if I go to the bottom, I've got 2 lines left. Ooh, excuse me, over here. I've got 2 lines left, nothing else joined to the hub, so I get that picture. So I've got a total of 8 pictures, 8 cases to draw from my 3 spans. Those are all the possibilities. The hub has to be connected to 1, 2 or 3 things, not more because there's not more lines, and not 0 because everything's supposed to be connected together. Okay, those are my 3 spans. By considering the possible sizes of the top group of tips, okay, let's have a look at the top group of tips in some of these cases. So they told us this was the top group of tips of size 3 up here. I've got somewhere the top could be just 1, or it could be 2 points together, or it could be all of the points in that kind of top group. Okay. Ooh, and different possibilities. If the even if all the points are in the same group, there's different possibilities for the span. Let's remember that. Okay. By considering the possible sizes of the top group of tips and how the group is connected to the hub, okay, calculate the number of 4 spans. Okay, so if I've got a 4 span, that's going to be some of the lines from this 4 fan with an F. Okay, so I suppose my top group might be all of the points, or it might be 3 of the points. It might be 2, or it might be 1. That feels like a natural way to split it into cases. Okay, so if top group is 4 points, and I've got my group like this, and I've got 1 line left over, because that's 3 lines. I've got 1 more line. There are 4 ways I could connect that. 4 ways to connect that to the hub. Okay, Okay, so that's one possibility. If the top group has all the points in, then 4 ways to join it to hub, I'll get four fans from that. Okay, they've told me to consider all the possible sizes. So I'm going to think about what happens if the top group is size 3. So I've got 3 points joined together, and then this point is not joined to the other ones. Okay, and because it's not joined up there, I suppose it must be joined to the hub. So now I've got to connect this to one of those. So I suppose there's 3 different ways to connect that group. I've only got one line left over, and there's 3 ways to connect. Okay, what if the top group is size 2? Then I've got 2, and then my bottom points down here might be connected or they might not. So I've got 2 ways to connect the top group. There's a pattern going on there. 2 ways to connect the top group. And then I'll have, after I've done that, I'll have 2 lines left over, and I need to sort out the bottom bit. But that looks exactly like the problem that I did before, right? Where I had a hub and 2 points, and I had to connect them using 2 lines. That was the number of 2 spans. Okay, so here the total is going to be, I've got a choice of which one of these I connect to the hub, and then I've got an independent choice of how I do this 2 span over here. So there's a 2 span over here. So my number of 4 spans out of this case is going to be 2 times number of 2 spans. Okay, last case is if my top group is just 1 point, then that's connected to the hub, and I've got 3 points left over, and I'm going to need I'm going to need to use 3 lines to connect this up. This is a 3 span, so this is the hash of number of 3 spans. Okay, so my total is going to be 4 from here plus 3 plus 2 times the number of 3 spans plus 1 times the number of 3 spans, which was 8. Number of 2 spans there was 3, and the number of 3 spans was 8. If I add that up, I get 7 and 6 is 13 and 8 is 21. I think that's right. Okay, so that's my number of 4 spans, 21 different possibilities. I like this way of working systematically. In fact, that's the rest of the question. Okay, so 21 4 spans. So we saw in the previous part of this question that there are 21 4 spans, and if I scrolled back up again, we would remember that there were 8 3 spans. We saw there were 3 2 spans. I suppose we didn't think about a 1 span. A 1 span's not very interesting. A 1 span says you've got a hub and 1 point, and you've got 1 line to connect them with. There is one span. Okay, I suppose the rest of this question is to try and find a rule for these numbers. 1, 3, 8, 21. I don't recognise those numbers. What's going on there? Okay, this part of the question, part 4, wants us to think about an expression for the number of n spans in terms of the previous values, where zk is the number of k spans for k between 1 and n, less than n. And we're going to use this relationship to work out how many 5 spans there are. Okay, let's think about that previous thing we did, thinking about the size of the top group. So we saw before that gave us a nice systematic way to break down the cases. We saw if the top group is size n, then, so if all the points are, in general, instead of 4, we're looking at n now, if in general all the points are in a group, then only there are sort of n ways to connect. Okay, that's a sort of generalized version of the first line I wrote down last time. If the top group has size n minus 1, then there are n minus 1 ways to connect it. Got to connect that group to the hub. And you get some choices. Well, not really, but you have that leftover 1 point. You have that leftover 1 point which you need to connect to the hub. I'm going to call that the number of 1 spans, because we have that idea that the leftover points felt like solving a small span problem. Okay, so connecting a 1 span. Maybe that'll make more sense when I think about that. If the top group is n minus 2, then there are n minus 2 ways to connect it to the hub. And independently of that, you get to join up the remaining 2 tips. they could be joined in any way that makes a 2-span to the hub. So you get some independent choices over here. You set up your 2-span below, and you can choose one of the n-1 points above, n-2 points above, to connect that group to the hub. Okay, this pattern continues until we finally get down to the case where we think about the top group being of size 1. Then there's only one way to connect it. And we're left with a huge number of choices. We're left with a number of n-1 spans for the number of ways to play around with the rest of the remaining tips below, joining them to the hub. Okay, in the notation of this question, the number of 1 spans is called Z1, the number of 2 spans is called Z2, the number of n-1 spans is called Zn-1, and the relationship that I've got here is the number of n spans is n, that's from the first case, plus n-1 times Z1, plus n-2 times Z2, plus and so on and so on and so on, plus 1 times Zn-1. Does that work out? So in each case, the number out the front multiplied by the subscript, the number out the front add to the subscript adds up to n. Okay, great. So this is some relationship that helps me relate the number of n spans to the previous numbers of n spans. Okay, use this relationship to show that Z5 is 55. Okay, let's keep this relationship, but clear some space out. Okay, so I want to use this relationship to work out Z5. It's going to be 5 plus 4 times Z4 plus 3 times 4 times Z1 plus 3 times Z2 plus 2 times Z3. Sorry, the numbers, the subscripts go up and the numbers go down. It's very confusing. 2 times Z3 plus 1 times Z... Oh goodness, 1, 2, 4. I've got confused again. There we go. The subscripts go up and the numbers go down. Right, okay. So this is 5 plus 4 times 1 plus 3 times, number of 2 spans is 3, plus 2 times 8 plus 1 times 21 is 5, 4, 9 plus 16 plus 21. It's going to be 9, 18, adding up, 34 plus 21 is 55. Oh, they're good, that's what they wanted me to show. Okay, this is a nice way to check, maybe, that we were onto something with these previous numbers, that we worked out the right numbers. Okay, let's put a note here, Z5 is 55. Right, okay. One last thing to work out. We're going to work out Z6. Using exactly the same method, we're going to go back through, very similar process, to add together everything from the previous numbers of fans, using this sort of recursion relationship to work out the value of Z6. Okay, Z6 is going to be 6 plus 5 times Z5 plus, no, 5 times Z1, same mistake again, 4 times Z2 plus 3 times Z3 plus 2 times Z4 plus 1 times Z5, which is going to be 6 plus 5 times 1 plus 4 times 3 plus 3 times 8 plus 2 times 21 plus 1 times 55, which is 6 plus 5 plus 12 plus 24 plus 42 plus 55 is some enormous number. 11, 23, 47, 89 plus 55 is 144. Some huge number of 6 spans. We saw one of them on the previous part in the setup for this question. 143 others. I'm really glad that I don't have to draw them all because that's the end of this question.